In this lecture, we'll discuss the autoregressive and the autoregressive moving average process. An autoregressive or AR process of order P is formed by feedbacking the output, earlier outputs, using again the shift register so that I will store them and I'll add up by scaling them to the input. That means that my output is going to be a sum of earlier outputs, feedback, plus an additive noise which we call the driving noise, the innovation process, that is the one that feeding in new information to the system. This is assumed to be a white noise with variance sigma e squared. And just as before, I will use the z transform to express this using a characteristic polynomial, a of z, which is again also monic, so that it starts with characteristic. So it starts with a 1. For this process to be stable, all the zeros of the characteristic polynomial expressed in z has to be inside the unit circle. You can see this by just thinking of an AR1 process like this, that the output is going to be the negative of the previous output plus the driving noise. Now, if the A1 here is greater than 1, that means that I will amplify my output every time, so that I will get a bigger YT and then the bigger and bigger for each time sample, so it will explode. So if I have my A1 here being larger than 1, that means my characteristic polynomial has my roots outside the unit circle, the polynomial is not stable, and therefore it is not an AR process. For an AR process, the roots must always be inside the unit circle. Using the notation of a characteristic polynomial, I can just divide down the characteristic polynomial like this. Now I have the transfer function here, it's going to be 1 over a, meaning that I immediately can see that the spectral density is going to be 1 over the magnitude square of the a polynomial evaluated over e to the I omega. Again, the notational confusion here is that it should be, of course, a to the I omega, but due to notational sloppiness, it's normally just expressed as a to the omega. From context, hopefully this is not hard for you to differentiate. The mean of an AR process is slightly more difficult to compute than the mean of an MA process. The way you see it is that I'll just move the expectation in like this, and if I express this as my, what I got is my times and then the characteristic polynomial, which is going to be a1 z to the minus 1 plus a2 z to the minus 2, and so forth, which is going to be equal to 0 because the driving noise is assumed to be 0 mean. Notice that this a polynomial cannot be 0 if I evaluate it on the unit circle, because the AR process cannot have any roots on the unit circle, because then it's not a valid AR process. That means that a of 1 cannot be 0, and therefore m of y must be 0. In order to form the autocovariance function, I will write out the AR process, and then I will just multiply by y of t minus k, and take the expectation on both sides. That is this expression down here. And if I move the y of t in here, you see that the first part I'll get will be ry of k, and then if I move it into the next step, I will get a1 y of t k minus 1, and so forth. The expectation of this side is going to be 0 as if my k is different from 0. And the way you can see that is that y of t minus k is going to have this form. And as you see, that this will only depend on e of t if k is equal to 0. That means that this is going to be equal to sigma e squared if k is equal to 0, and otherwise going to be 0. This is the Kronecker delta here, so it only takes the value 1 when k is equal to 0, and otherwise takes the value 0. This forms the so-called Joule-Walker equations, dictating how the A coefficients are bounded by the autocorrelation function. This is very helpful for us to and that allows us to estimate these coefficients very efficiently. If we look at an example, you can see that if I write out the recursive form like this, I can formulate the R of y1 like this, and I can find then by recursion, I can find the autocovariance function like this. If I want to find the autocorrelation function, I just normalize by R0, and I have the autocorrelation function. If I evaluate the characteristic polynomial on the unit circle, I get this form of the power spectral density estimate. This means that for any position in the unit circle where I have a root, I will have the corresponding peak in the power spectral density. And the closer the root is to the unit circle, the higher the peak will be. You can think of this as taking it to the limit, and if I put the root on the unit circle, that will make it into a sinusoid because of the Euler's formula, right? It's not an AR anymore, but then I would have a Dirac impulse. So the closer I am to the unit circle, the higher the peak is, and then in the limit it will turn into a Dirac. If I express the Joule-Walker matrix form, that is, I will take the R coefficients and I will multiply by the A coefficients like this, it should be sigma e squared if I have lag 0. If I have lag 1, I will get 0 instead. Of course, it's only the A coefficients that I care about, so let me call those theta. And thus I can see that 1 times the first column and then the next block times the theta will all be 0. And I get this more concatenated form of the Joule-Walker equation expressed in matrix form. I will call this matrix R of n, I'll call this vector little r of n, and of course this is what I called theta. This yields this equation, and just moving this to the other side and taking the inverse gives me the estimate of the autocorrelation coefficients. This means that I can form the estimate of the A coefficient by simply computing the autocovariance function, building this matrix, and computing the inverse like this. In general, it takes ordo n cube operations to compute an inverse. But in this particular case, this matrix has a very strong structure. It's tuplets. That means that all the diagonals and subdiagonals are having the same value. That allows me to form very computationally efficient algorithms. So that means that I can transform this into something that just takes order n squared operation. So I'm saving one order of magnitude in complexity by just exploiting the fact that this matrix has a tuplet structure. This is quite common, that you have very strong structures in your matrices, and if you exploit them, you can form computationally efficient algorithms. If you're curious to see how this is done, I recommend that you read the part on the Levinson-Durbin algorithm. Here's an example of an AR1 process. So this is the realization, and if I look at the autocovariance function, the things to see here is that does not go to zero as the MA process. It has a clearly ringing structure. It goes up and down here. And if I look at this power spectral density, you see that I have a power spectral density that is located predominantly at the high frequency, which means that I should expect the roots of my characteristic polynomial to have the roots there. And if I evaluate this, I'll see that this is going to be the case indeed. Here's an example of an AR2 process, and as you can see, I still have this ringing behavior in the autocovariance function. Then this is indeed something that we will use as something characteristic for AR process. Whenever I see that the autocorrelation function has this ringing behavior, that is something that should make me suspect that an AR model might be appropriate to describe the data. Looking at the power spectral density, you see that I have a clear, distinct peak at about 0.15. That means that I should expect the roots to be located like this. Check the characteristic polynomial to see that this is the case. Here's an example where I've computed the autocorrelation function of the data. Of course, the first lag will be 1 since it's normalized, but you can see there's a very strong ringing behavior, so I should expect this to be an AR process. And indeed, this is an AR4 process. If I estimate the AR coefficients using the Joule-Walker equations, I can find whether the roots are located at these two locations. As this root here is closer to the unit circle, I expect that this peak will be more pronounced in the power spectral density, which is indeed the case, whereas this one is further from the unit circle, and therefore the peak is going to be less pronounced. Please note here that I'm only drawing the power spectral density from 0 to 2 pi. That's why I don't see these roots. There will be, of course, the power spectral will, of course, be symmetric, so it should be looking like this if I draw the full spectral density. An autoregressive moving average process of order PQ is when I combined the two parts, so I have an AR polynomial and an MA polynomial. This is a quite general model, and according to Weierstrass' theorem, you can actually show that it can arbitrarily well approximate any continuous power spectral density as long as the model order P and Q are selected sufficiently large. Of course, here sufficiently large might mean that they're very large indeed, so from any practical point of view, that might be unrealistic to use anyway. And there will, of course, also be models such as pure sinusoids, which is not having a continuous power spectral density where it's not suitable either. But in general, it's a quite flexible model that can describe many forms of data, and it's also very useful for us in the modeling of time series here in this course. If I combine the results, I can see that the mean is going to be 0, and of course the power spectral density will be the combination of the two. If I compute the autocovariance function, you can see that it has the structure of the AR autocovariance function as soon as I pass model order Q, but up till then it will have some weird behavior. We'll come back to how to model this later on. In general, to estimate the parameters of an ARMA process is much more complicated than to estimate the coefficients of an AR because of the existence of the MA components, which is making it more difficult.